Hi, everybody. Sorry it's taken me a while to get this video uploaded. What I've decided to do is just finish up the section on 6.3, and we'll cover 6.4 in class tomorrow and Thursday, and then I will do a video over the weekend for you to watch on divergence and curl. Those are easier topics to cover, and I want to make sure we do the harder stuff in class, so we'll do it that way. So what I want to do is I'm going to share my screen with you, and we're just going to go through the last couple pages of the conservative vector field section. All right, so let me share my screen. Okay, so what we were talking about at the end of class yesterday was determining if a vector field is conservative, all right? So remember, a conservative vector field maintains the energy within the system, and it has some special properties. It means that there is a potential function, lowercase f, a scalar valued function of x and y, or x, y, and z, and the gradient of that potential function is the vector field itself. All right, now that's a pretty high bar to meet, but a lot of the applications that we study actually are conservative vector field applications. And so while it's not common for vector fields to be conservative, the ones we study, it is more common. So let's go through and talk about that property that if a vector field does not have it, then it proves it's not conservative, but it can't prove it is conservative. And that's the cross-partial property of conservative vector fields. So looking right here, hopefully you can see my cursor kind of bubbling around a little bit. So when we're looking at this, let me see if I can get it to go with a pointer. No, it's just going to do this. Okay, so let's suppose we have a vector field in 2D or 3D. And the components have continuous second order mixed partial derivatives. Now, let's suppose that it's a function of two independent variables, x and y. So we've got some component for the x, which is a function of x and y, p, and then we've got a second component, q, which is also a function of x and y. Now, if it's conservative, then it has what's called the cross-partial property. Just because it has the cross-partial, though, does not mean it's conservative. There are some non-conservative vector fields that do have the cross-partial property. But if it doesn't have the cross-partial property, it's definitely not conservative. And what we're going to figure out now is under what conditions does the cross-partial property guarantee that it is conservative? And there are some additional conditions we can add that will guarantee it. So the cross-partial means that if you take the partial of the first component with respect to the second derivative, y, it will be equal to the partial derivative of the second component with respect to the first variable, which is x. So the partial of p with respect to y is equal to the partial of q with respect to x. Now, when we have a function of three independent variables, so what you're seeing right here in the middle of the screen, it gets more complicated. In that case, we have to establish that it's got these weird cross partials. So remember, if it is conservative, then p itself is already the partial of the potential function with respect to x. So what we're saying is that the partial of f with respect to x and then y is equal to the partial of f with respect to y and then x. In other words, the mixed partials are equivalent to each other, which means it's continuous. So we do that for the three-dimensional case, which basically means that, again, we have to show that the partial of p with respect to y is equal to the partial of q with respect to x. But now that we have this third component, we also need that the partial of q with respect to z is equal to the partial of r, third component, with respect to y, and that the partial of r with respect to x, bringing it back around to the front, is equal to the partial of p with respect to z, bringing it back around to the end. In other words, all of our mixed partials are equal to each other. The partial of some potential function with respect to y and then z is the same as the partial with respect to z and then y, etc. Now, this is a very high bar to meet, all right? So it's not typical. But our question is, when is it enough for the cross-partial property to imply that the vector field is conservative. By itself, it is not enough. So what can we add to it to make it enough? And the answer is we need to guarantee that the domain is open and simply connected. In other words, open means it's not including the boundaries. Simply connected means if it's 2D, it doesn't have a hole in the middle of it, right? You can put that loop in the region and cinch it down to a single point and you'll never leave the region. If it's three-dimensional vector space, then what this means is that we don't have a tunnel boring through the space. So no tunnel connected to a boundary of the space, because in that case, we can't put a loop around it and close it down without leaving the space. Now, if we have a hole inside the three-dimensional vector space that's completely contained, that's okay, because we can get around that by just shifting the loop, but staying inside the region and then cinching it down. So the answer to our question is yes, there is a way to use the cross-partial property to prove that a vector field is conservative if the domain is also open and simply connected. All right, so path connected again means you can get from point A to point B in the region without leaving the region. So it's got to be open, which is easy to establish. It's got to be simple, can't contain a hole if it's 2D, and have a tunnel all the way through if it's 3D, and it has to be path connected. You have to be able to get from point A to point B within the region without leaving the region. Okay, so that's our next theorem on page 18, that if we have a vector field on an open, simply connected region and it has the cross-partial property, then it is conservative. So we have four conditions. Open, that's easy to meet. Simple, all right, simply connected. And connected, of course, is path connected. So simple, path connected, and cross-partial. Open, simple, path connected, cross-partial, then it must be conservative. Most of the domains we look at are open, are simple, and are path connected. Not all of them are simple or path connected, so that would eliminate a lot, but most of them are in fact open. So let's now take a look at, let's see, the other thing that we can prove using this is that if the domain is open, simply connected, so meeting 3 of our bars, and it has the cross partial, then it has to be conservative. It's an if and only if, so it goes both directions. All right, so now what we want to look at is example number 8. So looking at example 8, we have sine of x, cosine of y, cosine x, sine of y. Is it conservative? Well, okay, so first we look at the definition of the vector field, and we're like, well, what kinds of x's and y's can I put into this function and it be defined? Well, any real value. So it's defined on all of R2. R2 is by definition both open and closed, so that's fine. It's also a simple region. It does not have any holes in it, and it is path connected. I can get from any point in R2 to another point in R2 without leaving R2. So it's open, simply connected, and well, simple and connected. All right, we call it simply connected, getting 2 in 1. So now what we want to look at is, does it have the cross partial? If it has the cross partial, it has to be conservative. And if it's conservative, there's a potential function. So what we're going to do is we're going to come up here to the definition of the function, and we're going to take p, which is sine x cosine y, and take the derivative, the partial derivative with respect to y. So that would give us minus sine x sine y. And then we take a look at q, which is cosine x sine y, and we take the partial with respect to x, which would be negative sine x sine y, and we ask, are these the same? And the answer is yes, right? They are. Do not use this rule unless the domain is open, simple, and path connected. All right, those are requirements. So you've got to be sure that you check those. They're relatively simple to check, but you got to check. So we have a checklist here of all the steps that you should go through in order to integrate an integral, all right, a vector line integral. So when we're looking at this vector line integral, the first thing you want to know, or what you're trying to establish, is the vector field conservative? So the first thing you want to ask is the domain open and simply connected? Because if it's open and simply connected, the next thing you're going to check is whether it has the cross partial property. If it has the cross partial, you know it's conservative, and you can solve it using the fundamental theorem of line integrals. If it's not conservative, then we'll go back to the first method that we learned for evaluating vector line integrals. So first, we start with our question, is the vector field conservative? To answer that, we start with the domain. Is it open and simply connected? If it is, then does it satisfy the cross-partial property of conservative vector fields? So for a two-dimensional vector field, the partial derivative of p with respect to y has to equal the partial derivative of q with respect to x. And again, what we're really saying there is that there's a potential function, and f xy equals fyx. That's what we're saying. And then if it has three components, it's a function of three independent variables, the vector field, then we're trying to show that all of the second partials are equal to each other. So fxy equals fyx, fxz equals fzx, fyz equals fzy. So that's what we're getting at here with these mixed partials, right? Now, if the answer is yes, so for 2D, there's only one thing to check. For 3D, there are three things to check. It's not quite fair, but yeah, all right? If the answer is yes, it does meet the cross partial, it is conservative, then we go look for a potential function using the methods that we've already talked about. Once we find the potential function and we have a parameterization for that curve, then we don't actually have to do the vector line integral. We just use the fundamental theorem for line integrals in order to evaluate. But remember, this fundamental theorem of line integrals only applies to conservative vector fields. So we have to prove it's conservative first, all right? Now, if we ask, is the cross-partial property met, and the answer is no, then it's not conservative, right? If it's not conservative, then we have to use the definition of a vector line integral. So we're going to have to parameterize the curve and use the integral f dot dr, which is f of r of t dot r prime of t dt. In other words, it's the vector field dotted with the unit tangent vector with the arc length differential, which we have rewritten in the parameterized form that you see here. Now, what if our answer to the question, is the domain open and simply connected? What if that's a no? What if we have a hole in our two-dimensional domain? Or we have a tunnel in our three-dimensional domain? Or what if the domain consists of two separated regions and you can't get from point A to point B without leaving the region? So if we have one of those cases, then again, we have to do what we would do if it's not conservative. We have to parameterize the curve and evaluate it directly as a vector line integral. So let's take a look at example 9, which I believe is the last one in the notes. So this one is looking at the vector field sine x sine y and 5 minus cosine x cosine y. So it's a two-dimensional vector field, and we have that C is a semicircle starting at the point 0 pi up on the positive y-axis and ending at 0 negative pi on the negative y-axis. Okay, so our first question, what we have to establish, is it conservative? So to do that, we start with the easy part, the domain. Is it open and simply connected? Open, simple, path connected. Well, if we look up here at our definition for the function, there are no restrictions on x and y, right? They could be any real number. So that means that our domain is R2. Now, R2 is by definition open, simple, and path connected. So it's open and simply connected. So the answer to that is yes. Now we want to establish, does it meet the cross-partial property? It's two-dimensional, so that means establishing that the partial of p, the sine x sine y, with respect to y, is equal to the partial of q, the 5 minus cosine x cosine y, with respect to x. So we come down here, and we're going to define our p equals sine x sine y and q equal 5 minus cosine x cosine y. And we have to establish whether or not it meets the cross partial. We've already established it meets the first three: open, simple, path connected. Does it meet cross partial? So we take the derivative of sine x sine y with respect to y and get sine x cosine y. We take the derivative of 5 minus cosine x cosine y, the partial derivative, with respect to x, and we get sine x cosine y, and they're identical. So it does have the cross partial property, and that combined with open, simply connected, tells us that it is a conservative vector field. So there is a potential function, and we can use the fundamental theorem of line integrals. So now we're going to parameterize the curve, and we're going to go get our potential function. So this part doesn't apply because the answer was not no, the answer was yes, it is conservative. So let's go ahead and find the potential function first. Now remember that the gradient of this potential function, and we don't know what lowercase f is the vector field. So I do know that the partial of f with respect to x gives me p, which is sine x sine y, and the partial of f with respect to y gives me q, which is 5 minus cosine x cosine y. Of these two, p is slightly easier. So I'm going to integrate both sides of this first equation with respect to x and x only. So I take the integral of the partial of f with respect to x, and then I integrate sine x sine y with respect to x, and that gives me negative cosine x sine y plus some function. And this function could have constants and or y's in them, because as far as x is concerned, y is a constant. So now I need to find h of y. So in order to find h of y, I've got my candidate here for the potential function f. So what I'm going to do is I'm going to use this relationship right here to try to find this h of y that I don't know. So I know that the partial of f with respect to y should give me q. And since I think this is what f looks like, I should take the partial of this with respect to y and set it equal to q, which is 5 minus cosine x cosine y. So I set these equal. Notice that I get a negative cosine x cosine y on both sides. Notice that when you take the derivative of h of y, it's only a function of y. So it's actually the true derivative, not a partial, or the straightforward derivative. I don't know how you want to say it, but the first derivative, all right, of h with respect to y. So these terms right here, the negative cosine x cosine y's, if you add them to each side, trying to get them together, they cancel each other out, and we get dh dy equals 5. Now, if dh dy equals 5, I can integrate both sides with respect to y, and that will give me the integral of 5 dy, which is 5y plus some constant, right? So then I rewrite my potential function from here, and I substitute what I found for h of y. So I get my potential function as negative cosine x sine y plus 5y plus some constant, where the constant truly this time is a constant, 5, 11, square root of 32, something like that. Okay, now we can use the fundamental theorem for line integrals in order to evaluate. Now, to do that, we have to parameterize the curve. But quite frankly, no matter what method you use, you have to parameterize the curve. So you're not going to get out of that. You're going to have to parameterize the curve. So, and this goes through no matter what it is, you have to parameterize the curve. So just to make sure that you know to do that. So this is what it looks like starting at 0 pi and then going to 0 negative pi. So this is just a circle of radius pi. So we multiply the cosine t sine t by pi. That gives us a radius of pi. And we let t go between pi over 2 down to 3 pi over 2. So this is our parameterization right here. All right. The next thing that we're going to do is we're going to evaluate our potential function f at r of b and R of A and subtract them. So here's my potential function again that I found. And here is my parameterization. So the first thing I did was I took RB and RA and I plugged those values in. So RA is R of pi over 2. So if I plug that in here, I get 0 pi. And R of 3 pi over 2 gives me 0 negative pi. And then I take these values right here, my position vectors, and convert them into ordered pairs for the point at the end of the position functions. And I put those into the potential function, not vector, scalar valued function, the potential function. And that gives me this relationship that you see here, which gives me negative 10 pi, right? So this allows me to evaluate the vector line integral on that semicircle, right? So I'm getting the amount of work done in pushing a particle from one place to the other. Because it's negative, I must be going backwards to what we would expect. And so again, this is a way to evaluate work. There are other things that other applications have slightly different meanings, but that's one way to interpret it. So I'm going to stop here. Sorry it's taken so long to get this uploaded, and I will see you guys tomorrow, and we will do Green's theorem, and then whatever we don't get covered of curl and divergence on Thursday, I will cover all that in a video because that material is easier to grasp. Surface integrals, which is the next topic after that, is definitely not easy to grasp, and we have to do that in class. About the only topic left that I would do on a video is the divergence and curl, which is kind of a bummer for me because it's probably the most fun. So anyway, I'll see you tomorrow and have a great night. Bye.